Hey everyone, welcome or welcome back. Unit 2, humans versus bacteria, and we are still in our antibiotic resistance explain phase of our 5E. And don't worry, we're actually almost done, believe it or not. I know it's been a lot of information for sure, but we are powering our way through it. So we're going to continue explaining what antibiotic resistance means in bacteria. And just keep in mind, we're still trying to figure out how to prevent another cholera outbreak, how to prevent another cholera pandemic from occurring. And cholera is a bacteria that we see that has had 7 pandemics so far, and even one currently in El Tor, Egypt, right? El Tor is the longest one that we've had. And we're trying to figure out why it keeps coming back. How can we prevent another one from coming, a eighth, a ninth, a tenth one from coming back, especially when we thought we had gotten rid of it before. But it seems like it keeps coming back harder and stronger than ever. All right, so just keep thinking that in mind. Like, how do we stop this from happening? And our aim says, how do bacteria evolve to resist antibiotics? All right. And whenever we talk about evolve, we've annotated this before, right? It's a change over time. So, how do bacteria change over time to resist antibiotics? Now, Ardunal says two cultures, each containing a different species of bacteria, were exposed to the same antibiotic. Explain how, after exposure to this antibiotic, the population of one species of bacteria could increase while the population of the other species of bacteria decreased or was eliminated. All right. So if they were exposed to the same antibiotic, but they were two different species of bacteria, how come does seems like one of them their population seemed to increase even though they were exposed to it, but the other population seemed to dwindle, decrease, or have been thoroughly eliminated while being exposed to the same antibiotic? Well, one thing should definitely come up in our minds, and that is natural selection, right? And if we just keep in mind what natural selection means and we remember what nature cares about, it's the population's ability to survive and reproduce. So the population, I'm just going to put pop for short, that is increasing was able to survive exposure to the antibiotic. As a result, they were able to reproduce and pass on those genes of resistance to future generations. The other population, POP for short, may have decreased or been eliminated, eliminated. There we go. I knew I would get it because they lack the favorable adaptations, right, or traits needed to survive exposure and died. It's that simple. One colony had the favorable traits that they needed to survive the exposure, and so they were able to survive and reproduce and pass on those favorable genes to their offspring, versus the other colony, they just lacked those favorable traits to survive the antibiotics, so they died, right? Part A, natural selection reading. And again, whenever we talk about natural selection, we care about being able to survive and reproduce in a changing environment. Remember, we were first really introduced to natural selection this unit when we spoke about the rock pocket mice. Now we're talking about antibiotic resistance in bacteria, right? That is a changing environment for them. If we introduce an antibiotic to their environment, we've changed their environment and therefore are going to change how they behave or what they're going to be able to do in order to survive and reproduce or not survive and reproduce. Okay. So a change in environment doesn't have to be something that's huge and catastrophic. It literally could just be like a temperature change, right? Just like we saw with the marathon runner, right? There was a change in her homeostasis environment in terms of water balance and salt balance, where she drank too much water. And as a result, it changed the environment of her internal structures and caused hyponatremia, which could have proven to have been deadly for her. But let's circle back. So directions say read both texts below and annotate important parts of the text. So microbes in a cave text. So scientists find ancient cave-dwelling resistant bacteria in New Mexico. So 1,000 feet under the ground in one of the deepest caves in the country, scientists have found an ancient bacterium that is resistant to many of the antibiotics that we use in medicine today, right? So even though this bacteria has been tucked away, like literally tucked away from all of humanity, and we've been coming up with all of these great antibiotics, when we finally exposed it to the antibiotics that we were so proud of, it didn't die. It literally didn't die, right? So, I mean, it would go to show that naturally they are resistant to them. Luckily, the bacterium is non-pathogenic, meaning that it will not make us sick, right? So, whew, good thing that even if it does survive and reproduce these antibiotics, it's not harmful to us. So, reproduce on, bacteria, do your thing. However, it is puzzling that an organism that has been sealed off from human or even animal contact for more than 4 million years is able to resist modern antibiotics. That's incredible, right? They haven't had any contact with any other animals or humans in 4 million years. And they're literally resistant to the bacteria or to the antibiotics that we use today. It's mind-boggling, but it's so exciting, at least to me. I don't know, I'm a nerd. All right. In fact, they found one strain of this bacteria that is resistant to 26 of 40 antibiotics tested. So more than half of the 40 antibiotics tested, it was resistant to. Even brand new and powerful antibiotics were not able to kill off these bacteria. Whew, sounds like Mother Nature is really favoring these bacteria to survive. But let's continue reading on. How do bacterial populations develop antibiotic resistance at the population level? Let's read. Millions of harmless bacteria naturally live on and inside your body. These bacteria are the good guys, helping us in digesting food and fighting off other bacteria, which could be the bad guys. So I bet you didn't know that we have bacteria that live on and inside of our bodies, and they help us digest food that we otherwise wouldn't be able to digest. And they also help us fight off other bacteria, right? Because competition is never going to stop for resources. So they help us to fight off these other bacteria that are pathogens or harmful to us and that could really disrupt our homeostasis. So We owe bacteria almost everything. Let's continue. When harmful bacteria appear on the scene, your body's immune system can usually keep a small population of them under control. However, these bacteria reproduce too quickly, you suffer consequences. And this is called an infection. All right. So, our immune system does what it can to fend off or ward off a small population of bacteria. But if they're reproducing at a higher rate in which we're killing them, then we might need some help. All right. Antibiotics help your body fight off an infection by killing off those harmful bacteria. So now we need backup, right? Our immune system is saying, hey, we need to do, but this is a code red. We need some help, some extra assistance. That's when your doctor prescribes you antibiotics and they tell you make sure you take all of them and you finish the bottle, even if you feel better. Finish it, okay? All right. Now, introducing antibiotics into the environment of a population, like in the agricultural settings, places additional stress on bacteria, right? So when we introduce antibiotics to any colony of bacteria, it's going to create stress on them, right? They need to resist this in case they don't want to die. But if they don't have the favorable adaptations, then they will die and they can't reproduce. Like all organisms, bacteria are competing for resources and trying to avoid being killed by other bacteria or other organisms, like our immune systems, right? So bacteria are constantly competing for resources and trying to avoid being killed by other bacteria or by other organisms, right? Bacteria, believe it or not, they're kind of always under attack, much in the same way that they kind of attack other organisms. All they're doing is trying to get the resources that they need to survive and reproduce. That's really it. But as a result, it often causes infections in people, and unfortunately, some people don't make it because they don't have the favorable adaptations to resist the bacteria once they get inside and they start to wreak havoc and disrupt homeostasis. Let's continue. Through random mutations, some bacteria in a population just happen to possess traits that confer some resistance to an antibiotic, right? So through mutations, some of the bacteria, the individuals within the colony, within the population, have these traits that are just really excellent at resisting these antibiotics. That's all it's saying. When antibiotics are found in their environment, those with the resistance traits are more likely to survive and reproduce. The resulting offspring inherit resistance, therefore, the population over time evolves to be resistant because of this selective pressure, right? So that's important. Those with resistant traits are more likely to survive and reproduce. This is what we care about, the ability to survive and reproduce, right? And we'll define what a mutation is in a second. Let's continue. In natural occurring environments like caves, bacteria are also under stress and they compete with others for resources. Just like with resistance, random mutations may confer the ability to produce antibiotics to kill off competing bacteria. So this is really interesting. What they're basically saying is bacteria, many strains of bacteria possess the ability to produce their own antibiotic that kill off other competing bacteria that try to outcompete them for resources. That's really incredible, guys. That's really incredible. These bacteria are so efficient, even though they're so simple at surviving and reproducing, that they've developed ways of being able to produce their own antibiotics that help to ward off other bacteria that are trying to kill them, right? Now, these bacteria benefit from this trait, outcompeting other bacteria, reproducing more, and passing this trait on to offspring, right? So as a result of this, they're able to outcompete other bacteria because they have a little extra something something, their own antibiotic in the arsenal to kill them, right? So if we're going for the same piece of corn, I need to eat this piece of corn before you need to eat this piece of corn. So I'm gonna have to take you out and I'm going to use an antibiotic to take you out so I can enjoy this piece of corn so I can survive. And if I'm able to survive, I'm able to reproduce. And hopefully, my offspring will also have the ability to make their own antibiotics and outcompete so we can dominate the world, or at least dominate humans one body at a time. Let's conclude. At the same time, right, bacteria can evolve antibiotic resistance to the antibiotics being sent out into their environment by other bacteria. So even though some bacteria are able to produce antibiotics to kill other bacteria, they're not going to be able to kill every single bacteria that they produce antibiotics for. So those bacteria that are able to resist the ones that are producing the antibiotic will be able to outcompete them. This is like an arms race where competing species of bacteria try to kill each other and to invade their enemies at the same time, right? So I'm trying to like always dominate you. Think of imperialism, if you will. Thus, both bacteria that we encounter every day and those that we have never come in contact can evolve to become resistant to antibiotics. However, humans may be increasing the speed at which this occurs through activities like overprescription of antibiotics in humans and animals. So this last part suggests that humans are definitely causing these bacteria or helping these bacteria, increasing the speed at which they are able to resist antibiotics by overprescribing or overusing them. That's why it's so important that you only use antibiotics when you absolutely need them. If you don't need them, don't use them. Okay? Now, let's define some words here. One of the words we need to define is a mutation, which by now we should know what it is, but in case we don't, it's a random change in DNA. And why is this important? It's important for two reasons. It increases genetic variation of traits within a population, right? Increasing genetic variation is really important because natural selection needs variation, genetic variation, in order to work, right? And mutations are going to help that occur. It's also important because mutations can be beneficial, right? Just like how we see here, a beneficial mutation is the ability of these bacteria to now produce antibiotics. That is beneficial to them. They could be deadly, right? Where if we have like some type of like mutation that prevents us from being able to resist off these pathogens, these deadly bacteria, we don't produce like, let's say, antibodies for them, that can cause death for us. Or silent, which means that the mutation occurred, but it has no net gain or cost to us, right? We don't really feel the effects of the mutation at all. And then population, we've used this word quite a few times during this unit already, but let's make sure that we understand exactly what a population means, especially since natural selection only cares about the population. So it's a group of organisms that are members of the same species in a given area, right? So An example might include the number of people in NYC or number of MCSM students. MCSM students usually congregate at MCSM, and if you're a student, you belong to the population of students. If you're a staff member like myself, I belong to a population of staff members, such as teachers or so, right? But we are all members of the same species in a given area, so we're a part of the human population overall. That's all that means. All right, let's push on. So part B, natural selection comparison chart. So far we have seen natural selection in the rock pocket mice in terms of fur color, antibiotic resistance in bacteria in that agricultural video rather on farms. And now we just read a text about antibiotic resistance in bacteria in these caves. All right. So back to the rock pocket mice, which was where we initially started our natural selection journey, right? We just want to compare, right? In the rock pocket mice, what were our two variations? Well, our two variations were in fur color specifically, was light colored and dark colored. Those were our two variations, right? We had a mutation that caused some of them to be dark colored. What was the pressure in the environment or the change in the environment, right? There always has to be some type of changing environment if we're talking about natural selection. And the pressure or the change were the volcanic eruptions, right? And if we remember, the volcanic eruptions resulted in patches of dark colored, cooled lava, right, on the desert floor. That was the change. Remember, the entire desert floor was sandy, right? It favored the light colored, but then the volcanic eruptions occur and it had large patches of dark colored, cooled lava. Now, the adaptation is after the pressure or change in environment, the adaptation that we saw favorably was the dark colored mice. Natural selection literally favored the dark colored mice. And why did they? Because they were able to camouflage, right? If I have darker color fur, I'm gonna be able to blend in a lot better against a dark colored patch of land, right? I'm not gonna be seen by predators. So as a result, my differential survival and reproduction is going to be dark colored mice will survive and reproduce. What is this known as? Natural selection. Due to that environmental change, the environment now is selecting that the dark colored mice have the favorable adaptation. They have the one up on the light colored mice. And then the change in population over time, right? Because again, we care about the population, not the individual. The population of mice in the desert will become darker over time, which is what we learned in the investigation, right, is that the dark colored mice population seem to be increasing, whereas the light colored one seems to be decreasing. And it's probably because the light colored mice just don't have the favorable adaptations anymore. If the terrain is getting darker, then it would be a benefit for me to be darker in fur color so I can blend in a lot better against the new environment. Okay. So that takes care of fur color in pocket mice. Now, the antibiotic resistance in bacteria in or on farms, as we discussed before, right? What were our two variations? If we're talking about antibiotic resistance, they're either resistant or non-resistant. Pretty simple, right? You either resist the antibiotic or you cannot resist the antibiotic. What was the pressure or change in the environment? Well, the farmers administered antibiotics. So antibiotics introduced to farms by farmers, right? The environment would essentially be the same if they didn't add the antibiotics, but now that they've added the antibiotics, there's a change in the environment, there's a pressure in the environment. And what do we expect that to lead to? Well, our adaptation for this is the resistant bacteria will survive exposure to antibiotics. And as a result of having that adaptation, right, they will be able to pass on genes of resistance to approximately 100% of offspring. And why is it 100% of offspring? Well, it tells us here that bacteria reproduce asexually. And if we remember from our last lesson, we annotated that asexual reproduction just basically means that there's only one parent, there's only one bacteria, and that bacteria produces genetically identical offspring. So they pass on 100% of their genes to offspring. Now, the reason why we have approximately 100% and not exactly 100% is due to naturally occurring mutations that might occur and that often do occur, right? And mutations produce gene variation. So there might be a slight variation in the population of offspring that occur, but most of them will get exactly 100% of their gene variation from their parents passed down. And then finally, what we would expect over time for the population is that there's an increase in the number of antibiotic resistant bacteria on farms. We don't know if that number is going to go up to a 100. It's less likely that it will ever go up to 100 because nothing in nature is ever like at 100% really, unless we're talking about extinction in which 100% of the organisms in that population or in that species has been wiped out. But we do expect there to be an increase of antibiotic resistant bacteria on farms if we keep using them. Now let's move to caves, which we just spoke about, right? In the caves, we saw that these bacteria were able to produce their own antibiotics. So we have bacteria that can produce antibiotics or bacteria that do not produce antibiotics. Simple, right? What was the change in the environment? So humans never manipulated that. It wasn't a volcanic eruption that caused that, like the rock pocket mice, but rather it was a random mutation, right? In this case, it was a beneficial one, right? And the random mutation was antibiotic production, right? They were able to produce antibiotics from a random mutation. That was the change in the environment, right? Is that there was some type of mutation that occurred that allowed this to happen. Now it's going to change the way that they're able to adapt and behave, right? So the adaptation here is that bacteria that produce antibiotics outcompete, right? Which means that they're better suited to compete, outcompetes those that do not produce antibiotics, right? And as a result of that, we now have bacteria that produce antibiotics will survive and pass on the genes to produce antibiotics to offspring. Offspring as a whole, maybe not 100%, but maybe 99.9% sure. And as a result, the change in population that we would expect is an increased number of antibiotic producing bacteria in caves. So that's three examples of natural selection that we've literally gone through over the course um, of this unit so far. All right, now let us circle back. So what do we know about cholera resistance to antibiotics, right? We're trying to prevent another cholera outbreak. So we need to relate everything back to how we can do that. You might have discovered by now that bacteria are smart and sneaky. I've been repeating this forever. They can learn how to play the game and win it by becoming resistant to antibiotics, right? So the game is to kill these bacteria, but it's almost like they know what card we're going to play before we even play it. Oh, they're going to create another antibiotic. We're going to resist it. Yeah, we'll sacrifice some of us and some of us will die, but the majority of us will live. And let's see them try to defeat us, right? Cholera has been playing this game for over 200 years and have come back 7 times in those 200 years already, as we learned in the unit opening, right? Antibiotics are drugs that work by killing or stopping the bacterial growth. As you have seen in the video in this unit, the more we use antibiotics, the more bacteria can become resistant to them. So this is an example of something causal. It's telling us that the more we use antibiotics, the more bacteria can become resistant to them. That is true, okay? Also, you might have discovered in our investigation, when we take antibiotics, the sensitive bacteria are killed first, while the ones with the resistant trait survive and they can pass that trait to new bacteria, increasing the bacterial population. This is also causal, right? Because not just in our investigation, but in real life, when it's not a simulation, that's exactly what's happening inside of our bodies, right? We saw that in the investigation. If we only take our antibiotic regimen for some of the time and not for the entire 7 days, then we saw that the resistant bacteria, they were going to start reproducing and wreaking havoc. But for the majority of us, if we took all 7 days, we were able to kill off the infection, right? So that is causal. Now, is cholera resistant to antibiotics? The short answer is yes. Now we're starting to maybe see why they kept coming back, right? Cholera is one of the bacteria that over the years has become resistant to antibiotics. While in the past, many antibiotics were able to easily treat cholera, recently scientists have noticed that treatment failed because the cholera bacterium acquired the resistance trait for antibiotics, right? So this is also causal, right? Treatment failed because the cholera bacterium acquired the resistance to it. Right? If it didn't, then we'd still be able to use antibiotics to kill them, but apparently they're resisting it. Scientists believe that the resistance to antibiotics in cholera, so scientists believe, whoops, switch back to highlighter. The resistance to antibiotics has been caused by the overuse and misuse of antibiotics in several sectors, so health, agricultural, and food. This is actually an example of correlational evidence. We haven't determined this yet. This is correlational, right? And we can see that because it says scientists believe. It's not saying that scientists have determined or that it's 100% true or caused by, because, right? All of those represent a causal. But when it says that scientists believe that it may have, that it could be, all of that is correlational jargon. All right. And that's essentially telling us that they believe that it may have been caused by the overuse and misuse. So even though it says that it may have been caused by, it still says may have been. There may be so many other factors that's influencing why bacteria are being resistant to it, besides the overuse or the misuse of antibiotics in several sectors. Let's continue reading. So, for example, 12,000 refugees in Zaire, Africa, died in 94 because of antibiotic resistance cholera. This is This is causal. Right? It's telling us that 12,000 refugees died because of antibiotic resistant cholera. So we do know that these cholera are antibiotic resistant and that it is deadly because it killed 12,000 people in Zaire in 1 year, 4 times the number of deaths of the 9/11 attacks in NYC back in 2001. Antibiotic resistance is a serious issue that must be addressed if we want to treat and cure people when they get any type of bacterial infection. So how does cholera become resistant to antibiotics? In 1992, a new strain or type of cholera showed up in Southeast Asia that was resistant to 4 different types of antibiotics. When scientists studied this new strain, they found out that it came from the original cholera bacterium that acquired the resistant trait? This is causal, right? And we know that because it says that when they studied it, they found out, right? This is true. They found out after they researched that it came from an original cholera bacterium that already had the resistant trait. So if it came from it, that means that it was passed down, right? So that's causal. Because that original one was resistant, the new one is now resistant. How do bacteria acquire resistance traits? There are two major ways. The first one we've spoken about extensively, which is random mutations. As you learned in the rock pocket mice investigation, mutations can be responsible for the creation of new traits. And if the trait is advantageous, like antibiotic resistance, then the organism can survive and reproduce and pass that trait on. Over generations, the population with the advantageous trait increases, right? So the random mutation created dark colored mice, right? But then there was an environmental shift where it went from not being advantageous to now being advantageous after the volcanic eruptions. And now the dark colored mice population are able to outcompete the light colored mice population. So over time, we expect them to become darker, which is exactly what we literally saw here for the fur color in pocket mice. That's what these components are explaining. And then the second way is a very interesting way, which is DNA exchange. Interestingly enough, cholera prefers this strategy over random mutations. Let's see why. With DNA exchange, different strains of bacteria can exchange parts of DNA, called plasmids, that possess the resistance to antibiotics. For example, a cholera bacterium that is resistant can share a plasmid with another cholera bacterium that is not resistant and provide it with resistance of up to 6 antibiotics. Similar to when you play a video game and you share your resources with another player to help him or her survive in the battle. Guys, that's really incredible. Believe it or not, that's a form of sexual reproduction. They're exchanging DNA between each other, right? Creating more genetic variation. So one cholera bacterium that is resistant is basically saying, listen, I know you're not resistant, but I'm going to help you out. Take this and you'll be resistant to those pesky humans that are trying to kill us with all these antibiotics, right? So no wonder why it prefers that over random mutations. I don't want to sit around and wait for a random mutation. I want to go ahead and be proactive and exchange DNA with my fellow colleague, my fellow bacterium, and be as resistant as we can possibly be. Okay? Let's conclude. So it says either because of DNA mutations or exchange of DNA between bacteria, antibiotic resistance is becoming more and more common among several bacteria. That's causal, right? We definitely do see that bacteria are becoming more resistant over time. Scientists are running out of antibiotics to use to treat infections, and more people are dying because bacteria are resistant to antibiotics. Do you think antibiotics can be the solution to preventing a future cholera outbreak? Remember, we still have to answer this question. How do we prevent another cholera outbreak? And everything that we've learned about antibiotics and their uses, their misuses, using them on farms, finding them in caves, and the benefits, the costs, like, do the benefits outweigh the costs, right? Should we use antibiotics to prevent another future cholera outbreak, to prevent cholera outbreak number 8? I don't know. It's up to you. All right. So let's wrap up. Number one says, describe one example of evolution by natural selection that we have discussed in class. And you guessed it, I'm going to leave that one up to you. We've discussed several ways of evolution by natural selection that we have discussed in class. Think about the simulating a bacterial infection investigation, the caves one, all of that kind of stuff. Number two, how can we evaluate a claim about the cause behind um, a phenomena, right? So if the phenomena is being able to resist antibiotics, how can we evaluate a claim about that? What are some ways in which we can navigate how to evaluate if the claim is supported, if it's refuted? How can we go about doing that? And number three says, how can we use evidence to differentiate between causality and correlational? Discuss one example from class, right? So I'm not going to give you the examples, but I'll help you out with a working definition of causality and correlational, which we've been highlighting a lot. So causality just means cause and effect. One factor directly causes the effect, right? Which is the outcome. Right? And then below that, you can put your example. And then correlational just basically means patterns, right? Nothing that's directly affecting, but there may be multiple factors that contribute to the effect or outcome, right? And then you're going to provide an example there. And then number four finally says, when discussing the evolution of antibiotic resistance, what patterns did you observe? How did these patterns help you understand the possible causal relationships between using antibiotics in agriculture and widespread antibiotic resistance? Okay. I know these questions sound a little tough, but just work your way through it and you guys totally got this. We have one more elaborate lesson, just one more, and then we are absolutely done. We are done. All right. Which means you have a performance task coming up after the next lesson. So I'll see you guys next time. Bye.